Alright, and welcome to this video where we're going to do, we're going to present the selection sort algorithm, and then we'll do some analysis of the algorithm. Alright, so selection sort is again one of the three most common of the n-squared sorting procedures, and it is pretty easy to understand as well. The idea behind this one is we're going to find the minimum element, and then we're going to just swap it into the location, into the first location, and then we're going to repeat for the second minimum element and the third minimum element and so on until we've put the list in order. So we can actually take a quick look at the code that we've written here. Again, this is Java code using a simple swap subroutine that will swap two indices for us. All we're going to do here is, again, the outer loop is going to control which minimum we're going to be looking for, and the inner loop is going to find the minimum. So let's be careful here. So we're going to start out our outer loop with index 0. So we're going to set our, we're going to initialize our index parameter to I, which will also be 0 at this step. Now index is going to keep track of the index of the minimum element, and in our first pass we're going to find the minimum element over all possible elements. So we initialize it to the first element, we begin at the next element, and we iterate to the end of the list, and if we find an element that's less than the one that we currently have, we just update our index. So a very standard minimization procedure here. And so at the end of this loop, index will be the index of the minimum element, and we will swap that element into the first location. On the next iteration, we start at position 1 instead of position 0, and we'll find the minimum of the remaining elements. Okay, so this is again a fairly straightforward sorting procedure, hopefully one that you've had a chance to see before. But the purpose of today is to try and complete the analysis so that we can come up with a good estimate of its runtime. Specifically, we want to find a good big O bound of its runtime. So again, I mentioned at the beginning of the video, this is an n-squared sorting procedure, so at the end of our analysis we should arrive at an n-squared solution. Alright, so I have the sum written here for us to work with. And again, there's a couple techniques that we can use to do this. I think my goal here is I'm going to distribute that sum over. That's, again, my intuition at least is to distribute that sum. So we'll get our first sum, I equals 0 to n minus 2, of a, plus, now again, our double nested sum. The outer one is still going to be the same indices, I equals 0 to n minus 2. And our inner one, again, same indices, j equals I plus 1 up to n minus 1. And the constant that we're summing over here is b. All right. Again, we might want to factor out the constant that does not depend on our index that we're summing over. A does not depend on I, so we can move it out front. All right, after factoring out, the a has come out here, and the b also does not depend on the j nor the I, so we can factor it all the way out to the front there. All right, leaving us with a couple of sums that we might be able to simplify. This one's going to be the easiest, starting at 0, going up to n minus 2. That gives us n minus 1, so we'll have our a times n minus 1. Our second sum here maybe not so easy, so let's leave our b here. The outer sum I'm just going to leave alone. And then the inner sum we want to look at closely here. Well, again, let's maybe go to some scratch here. We are only just summing over 1, so we want to know how many 1s there are. Well, we take the upper bound, n minus 1. We minus off the lower bound, which is I plus 1. And then we add one more to figure out how many terms in the sequence. So that's going to give us an n minus a 1. It looks like a minus an I, minus a 1, plus a 1. So maybe we'll cancel 2 out, and maybe I'll write that here as n minus I minus 1. Okay, now it's at this point where we have a couple choices that we could do for how we want to continue this. We can continue with maybe the straightforward way, distributing this sum over. That's going to give us 3 sums, 2 that are not too difficult and 1 that has the I in it, which means we might need to remember that solution. But again here, there's another solution here, which is we can reverse this sum. And to reverse this sum, we need to think, okay, what values is this sum going to take on? So I'm going to go ahead and calculate this. I'm going to say, if I plug in my 0 here, I'm going to get n minus 1. If I add 1, I'm going to get n minus 2, and so on. And the last one I'm going to get is this n minus 2. Okay, so let's be careful here. When I plug in the n minus 2 for I, that's going to be an n minus an n, but then a plus 2 minus 1. Plus 2 minus 1, that gives us 1. So it looks like the values we're actually summing over are the values from 1 to n minus 1. So now I can rewrite this sum. And after rewriting the sum, we get this sum here, which is the reversal sum. And we can again maybe go to our notes and remember what this sum is equal to here. So again, recording the first value, a n minus 1, plus now this whole sum, while we've still got the b there, this whole sum is going to be n times n minus 1 all over 2. Again, that's an arithmetic series, or Gauss's sum. So hopefully we have that in our notes, or we've remembered that. And maybe we can simplify out a little bit. So we get an minus a plus bn squared. Looks like minus a bn, but each one of these is over 2. So if we do want to simplify it all the way to the end here, we can finish off with, let's bring our n squared up front, isolating its constant coefficient as b over 2. Then we have an n term, and I usually put that as a plus. Let's see here, plus we're going to get, there's an an, there's going to be a minus a b over 2n. Oops, let's write it like that. And then that leaves us with the one term, the minus a. Okay. Again, the goal of this analysis was to come up with a big O bound, and since our dominant term here is n squared, we get n squared as our big O. Okay. So in conclusion, we've actually in the last series of videos looked at 3 different sorting procedures. We've looked at bubble, we've looked at insertion, and we've looked at now selection. And all 3 of them, after a little analysis, we found that they were all, in the worst case, they are all n squared algorithms. This maybe raises an interesting question. Well, what about the best case? What happens in the best case to these algorithms? And to do that, I'm going to revisit each one in turn. If you remember in the bubble sort algorithm, we actually have a early exit criteria. That is, if the list is found to be already sorted in one of the passes, then we will exit early. So the best case for this, so if we're going to looking at best case, the best case for our bubble sort is actually linear. If we give bubble sort a already sorted list, it will make a single pass over the list, and then it will register that the list is sorted and complete. If a sorting procedure has a best case solution that is order n or better, we have a term for these sorting algorithms. We call them adaptive. And bubble sort, even though it's fairly simple, it has an n squared worst case running time, and sometimes that's something we want to avoid. If you give it lists that are mostly sorted or already sorted, it's actually very fast, and so that's one reason we like it. It turns out this is also going to be true for insertion sort if we've implemented it properly. If all the elements are already in place when we encounter them, there will be no shifting backwards to put them into their location, and again we'll have an order n best case runtime. The algorithm we just looked at, though, selection sort, because its inner algorithm is to find the minimum element, even if the minimum element is in the first location, it still needs to check that element against all of the other elements in the list. So unfortunately, select does not have a best case of order n. It has the best case of order n squared when run with just a normal list. And so as a result, maybe it's not as great when we're considering already sorted lists. An already sorted list is still going to take just as much time as a completely unsorted list or a random list. All right, well, in most of the cases, we're more worried about worst case performance. And all three of these have n squared worst case performance. And so because of that, we tend to lump them all together. But if you have to choose one over the other, sometimes you're going to see we favor maybe a bubble sort or an insertion sort because of their best case runtime. Okay, that brings me to the end of the discussion of our n squared sorting procedures. There are some others, but these are the ones I wanted to include in this series of videos. And in the next video, I want to bring in the merge sort algorithm. The merge sort algorithm is different in that it has an log n runtime, which of course is an improvement over the n squared. And I will present some analysis next day or in the next video of that algorithm. All right, that's it for this video, and we'll see you in the next video.